Hello everyone, this is Bowen. Today I will show you our study on microgrid frequency stability. First, I will introduce the issue of grid frequency stability due to grid connected converters. Then I will show you our models to predict the stability conditions. Finally, I will introduce our testbed and the experiment to verify our analysis. What you are seeing now is a factory located in a rural area. The factory is supplied by a 1 per unit distribution transformer and 1 per unit bus feeder from the diffusion power grid. Now, the factory owner needs more electricity energy due to the newly installed 8 per unit electrical drive. To avoid bothering the utility to upgrade the grid distribution system, the owner installed PV panels and wind turbines and energy storage devices. They are connected via several power electronic inverters. This DG represents all these inverters. This example reflects the concept of future distributed generation system. However, when the factory starts running all the power converters, it is found that output frequency of inverters start oscillating and eventually the whole system collapses. To understand the instability issue shown before, we can represent the system by this diagram. Converter 1 represents the distributed generator which gives the energy to the local load and the grid. Converter 2 represents the motor drive with active front-end rectifier. These two converters, together with local load, are connected to the grid. The three-phase grid also have some impedance represented by ZG. Each converter needs phase-lock loop to synchronize with the grid. Each PLL gathers the same voltage information at the PCC point. Thus, PLL loops are coupled together. Under the weight grid condition, different PLL design will lead the system to unstable conditions. Small signal model of PLL loops are derived for the system. We can see that the two PLL loops are coupled together. Each PLL gathers the information from other PLL and the grid information. The system stability condition can be studied by using signal flow graphs. We can see that in this system, two converters are coupled with the grid. The transfer function of this system can be obtained by using Mason's gain formula, and we can study the characteristic equation of this system to predict the stability of this system. Now, let's take a look at the test system. In the test system, we have two converters, and the local passive load connect to the grid. These two converters have very different PLL design, which highlight in the purple circle. And this system is an unstable system, which oscillation frequency is 1.47 Hz according to our models. Now let's take a look at the test bed for our experiment. This is a inverter which represents our distributed generator. It has a DC source which mimic the PV panel. This converter represents the motor drive front end. And here you can see a switch which is the PCC switch. There, 3 wires connect to the grid, and that load back is the local load. And here is the DC source which mimic the PV panels. Now we powered up our test bed. This test bed has two converters, and these two converters are controlled by one single digital control board. Now keep a look at the oscilloscope. We are monitoring 4 signals. The first green one is the PCC grid voltage, and second one is the inverter output frequency, PLL output frequency, and the blue one is the rectifier input current. The yellow one is the inverter current. Now the inverter is not running, but the rectifier is already connected to the PCC and is working on diode rectifier mode. When we start the first converter, you will see the inverter current in sinusoidal. And when the rectifier starts, the system became oscillating.